In this section, we're going to talk about stoichiometry and heat of reactions. As you can tell, stoichiometry is something that reappears throughout this entire semester. And again, it simply means the relating of amounts inside a chemical reaction. So this time we're going to be relating the amount of a substance in the chemical reaction to the heat that's generated. So the heat of reactions per mole. And so if we can convert a mass to moles, then we can relate the amount of heat per mole of reactant. So the process is we're going to go both directions. So starting out, we're going to have a mass of a substance, change that to moles using the molar mass, and then using the enthalpy of reaction, we're going to get the kilojoules of heat. But we're also going to do a problem in which you're given the kilojoules of heat and asked for a mole. So in this direction, we're dividing by molar mass here and multiplying by this. If I'm going backwards, then I'm going to do the opposite. So I would be dividing by this and multiplying by that. So when I go this way, this one, oops, I know that's not the color I want. Okay, so in this direction, oops, that was really bad. I'm going to divide by molar mass and then multiply, oops, I'm not having good luck here, multiply by delta H. If I go in this direction, then I'm going to divide by delta H and multiply by molar mass. So if I reverse the order, then I reverse the mathematical signs. Okay. So the first problem is hydrogen sulfide is a foul-smelling gas. It burns in oxygen to form sulfur dioxide. So here's my balanced reaction. Now with stoichiometry, we've done this before. The fact that this thermochemical equation here says that negative 1036 is per 2 moles of H2S, per 3 moles of oxygen, per 2 moles of SO2, and per 2 moles of water. So I can say that, just to relate two of these, that I have negative 1036 kilojoules per 3 moles of O2, and that's equal to a negative 1036 kilojoules per 2 moles of SO2 for this equation. So I take whatever the delta H is and divide by the coefficient in the moles of whatever that identity is. So in this one, it wants to know what the enthalpy change is for the mass. So if I go back to the previous slide, we're going from mass to kilojoules. So we're going to divide by molar mass and we're going to multiply by delta H. So I have a mass of 28.5 H2S. They want to know what delta H is equal to. So the first step in that was to divide by the molar mass. I need to find the molar mass of H2S, and I'm not going to break it up into steps, but it's the same thing as 2 times the hydrogen plus the sulfur. So the molar mass is 34.08 grams per mole. We've been doing that a lot this semester. And so to find N, or the moles, it's the mass divided by the molar mass. So it's going to be 28.5 divided by 34.08, and I get 0.8363 moles of H2S. Okay, and then the second step was I want to get just kilojoules and to cancel out this, so it's going to be N times the delta H, so it's going to be 0.8363 moles times the negative 1036 divided by, the coefficient here is 2, so 2 moles of H2S. And so I'm going to take this times that divided by 2, and when I do that, I get a negative 433.2 kilojoules. Okay. The next problem is ethanol mixed with, again, burned with oxygen, forms carbon dioxide plus water. So anytime I combust an organic compound, I get carbon dioxide plus water. I have Q, or technically it's Q, is 358 kilojoules. I have a delta H that's a negative 1235 kilojoules per, this is interested in methanol, so per 1 mole of C2H5OH, because the coefficient here is 1. And they want to know what mass do I need to generate that heat. Okay, so in this one, going back 2 slides, I'm going in the opposite direction. I'm starting here. So I'm going to divide by the delta H and then multiply by the molar mass. So, or if I think about it, and I don't know which process, okay, just looking at the units. Typically, the safe thing to do is always start with the one that's not a conversion unit. Okay, this is not a conversion unit because it's only 1. This is because this is kilojoules per mole. So a conversion typically has, or always has, at least 2 units to it, versus a non-conversion only has 1 unit. Now, the negative sign just tells me that this is exothermic. It doesn't have anything to do with math, okay? So I can either make this a negative 358 or I can drop the negative altogether. I'm going to drop the negative altogether. So I have 358 kilojoules. So this is back to like the dimensional analysis. There's really not a formula that we're using. And I have 1235 kilojoules per 1 mole of C2H5OH. Okay, so when I'm using dimensional analysis, this unit goes on the bottom, this goes across whatever the horizontal line is. And when I do that, I get 0.2899 moles of C2H5OH. And then to go from moles to mass of something, so the mass is simply the moles times the molar mass. So the molar mass of C2H5OH is 46.08 grams per mole. Again, not showing that, but it's 2 times carbon, 5 times hydrogen, 1 oxygen, and 1 hydrogen added together. So my mass is going to be the 0.2899 times the 46.08, and that gives me 13.4 grams of C2H5OH. And that is the end of this video.